Okay, welcome back. I think we will continue with our part 2 of our chapter 3 on thermal control. So as I've stopped here the last time, we'll look into basically the hardware now. What are the options that we have? This graph basically shows you the actual heat transport performance. The higher heat transport performance that you want, technically you need to be in that this region. I will explain a bit, and versus the operation life. Now, operation life, I have actually very open here. I will actually give you an example, basically in an attachment together with the lecturer's note. But again, it all depends on the manufacturers. So there are multiple manufacturers have a different specification, different operational, well, I would say duration, and a different kind of performance. So we can't actually just put them all together in that sense. But essentially, what is important here is that to look at actual performance that you have. Okay, what it says that if you have a mechanical two-phase loops. So loops, what it says that the typical hardware that we're looking at for thermal control are basically, you can imagine that it's just like a pipes, okay? A pipe with a fluid inside, transporting heat from one spot to another spot. That means there's a liquid is flowing. So you can just imagine that's how actually we're going to see that examples. So when you have, there's two ways actually you can do this. One, to let it happen naturally. How the naturally it can happen is that when you have a heat from one spot, basically that spot will get heated up. When you get heated up, a kind of a very special kind of design that we have, capillary designs. So capillary designs is that if you look at the actual cross section of that duct or the pipe, you will have grooves. So these grooves on the wall are going to actually give you the capillary effect. What is the capillary effect? Is that when the particular fluid, basically the water, maybe ammonia, it is heated up. So what exactly will happen is that it will evaporate, and the evaporation basically happens towards the wall, retracted, and then the flow is actually created. That's how. But you need to have the heat. Without the heat, nothing. There's no change of phases. Basically, liquid will be actually liquid. So the evaporation will take place. Place called the evaporator that we will see later. So then it goes on the flow. So there are two phenomena that we observe here. One is thanks to the capillary effects that we have. Another one is the typical surface tension. I think all of you have heard that surface tension of the particular liquid. So both these actually effects complement each other to make sure the fluid is flow. So there is no pump actually needed. Now, if you want actually a very good or very high amount of heat transported to a particular spot from point A to point B, then you want to maybe look at the option of having a mechanical pump. So you can imagine I have a pump pumping the fluid from A to B. Can you imagine? It will be very fast flow. Just like imagine yourself, you have in your car, you have a radiator, you have the fluid system, cooling system. You have basically a water pump which actually pumps that actually liquid to create a flow. So if you have a pump, basically it's going to be very fast in terms of cooling. So, but again, very good performance. But problem is that you have a pump. When you have a pump, you need electricity. When you have a pump, you are going to actually create micro vibration within the spacecraft. It's also not very well, I would say desirable. So unless you really need it, maybe in a space station, yeah, places like space station, you need that cooling system. So in satellites, low-cost satellites, for example, you don't want to actually have a pumping system basically to pump the heat out, because it's going to cost you vibration, micro vibrations, and it is going to cost you electricity. The complexity is increases. Okay. Now, these are the other examples. We have single phase loop. What actually by single phase loop? It says that there is a phase change. There's a phase change from one phase to another phase. That would be actually a single phase loop. That means it's water remains as water. From one phase to another phase, it actually remains as a single phase. Okay. but sometimes you have a capillary pump two-phase. Now two-phase is basically, you can imagine, liquid water, let's say, becomes vapor, vapor becomes back, get condensed, becomes liquid. So there's two phases. So you have this, either this option or these options, okay? And you have a high capacity heat pipes. Heat pipes, you can imagine, it's again, what are heat pipes? Heat pipes are basically a loop of a system consists of a liquid or fluid which transport your heat from point 1 to point 2. Simple. We will also provide you that data sheet of heat pipe for your reference with this notes. Then you have types of heat pipes basically for satellites. You have, this is actually fixed conductance heat pipe. This is variable conductance heat pipe, meaning fixed, that means the transportation, let's say you have an, well, a particular distance, the conductance of it, that means the capacity of heat rejection is fixed throughout the system, or you can have multiple kind of conductance. That means the conductance can be different. Let's say one spot you have an simple aluminium, another spot you have basically enhanced cooling system which transports slightly more. That means the exposed area is actually larger. Therefore, basically the conductance will be also altered, different. So remember, the conductance also is a function of the actual distance of cooling. So if you don't have, you may have a constant one, or you may have a different or other variation one, or variable conductance. You can have 2-3 spots. Spot A, conductance is different. Spot B, conductance is different. Spot C, conductance is different. Variable conductance. You can have that depending on the actual requirement that you have. Remember, all the subsystems have different operation region, different temperature generated. So you can have a different conductance, a variable conductance heat pipe as well. So it depends on the actual, but these are the types that you have. Another one, passive control system. Passive control system, thermal control system are practically, if you don't have, you have a heat pipe. If you have a heat pipe, then if you don't fix a pump to the heat pipe, it is going to happen through the flow is going to happen because there is a heat, and because of the capillary effect that you have in the heat pipe and the surface together with the surface tension of the liquid, technically you are going to actually have a very passive flow. Remember, heat is going to flow from hot spot to a colder spot. That's how the heat works. So that transportation works without electricity. If you want it to be fast, you put a pump. When you insert a pump, then it is going to be an active type. A passive type of thermal control system, not only heat pipes, but also insulations, like blankets. You have the thermal blankets, we call it. So thermal blankets, later we will discuss that, thermal blankets. So thermal blankets also we can use basically to protect any radiation from outside, any heat from outside. We can actually have a thermal blanket. Imagine if you want to maybe bake something, you have that aluminium foil, you have well, the food inside, and then you wrap it up. That is actually going to contain a lot of heat inside. So that is also a thermal control, passive thermal control method. Go on. Okay, look at the passive system. So passive system is good because I don't need any electrical power. When I have a thermal system, I need electrical power. What I must have? I must have a bigger battery. I must have maybe a bigger solar panels. So my mass gets bigger, my volume gets bigger, and obviously my cost is going to get bigger. So it's good to avoid fluid mass flow or line mass flow. So fluid, basically there's a fluid actually is flowing practically. Line mass flow, that means there's a huge amount, there's a reservoir, and then from the reservoir basically there is a fluid flow. That is actually called mass flow already. Okay, but fluid lines basically you have just like the heat pipes. You have thin loops looping to just actually to reject the heat. You will see that as well. Status, there is a sensoric. Basically, normally you have a thermometer. Well, technically, thermometers basically that you should be having thermometers to look at the actual temperature to monitor and the control equipment. So you don't need all this basically for a passive system. So can you imagine? I don't need to worry about the control system. I don't need electricity. I don't need any thermometers around that to constantly monitor the temperature because it happens naturally. So other options I have, well, if passive is that, and exclusively is only if basically uniform temperature environment. Technically, very small kind of well, relatively small satellites, almost not much of temperature, high temperature gradient. Typically, inside generated temperature also is lesser. Remember, I just mentioned last time that if you have a very high power consuming equipment, thermal control is going to be tough. So you have a low power consumption inside, so it will be a very easy job basically for a passive thermal control system. Low internal dissipation, as I've said, and low payload and equipment demands temperature. So when you keep that very small amount of actually power consumption internally, more often than not, you can be happy with the passive thermal control. One. Now, what you see here is a passive thermal control systems that is available for space application. All, whatever you can imagine for not only satellites, for any other application you have. Now, I go one by one. Typical one, please. Thermal insulation, multi-layer insulation. We're going to highlight this because this is very typical for satellites. The rest, yes, there are usage as well. Okay, important multi-layer insulation. For example, if you look at a satellite, sometimes you look at all these wrappings of, it looks like a very gold kind of wrapping. That is actually is a multi-layer insulation. It's called Krypton. Sorry. Then you can have also mylar. It is aluminium kind of base. So you can have this multi-layer. You have a Krypton layer on top, then you have aluminium layer. So there is quite a thick, not very thick, but two to three layers basically for you to do insulation. Or you can see you have a single Krypton layers. It's just like a gold color. You wrap it, and that is going to actually help you in terms of radiation, to protect you in terms of radiation. That means the external radiation to enter, any heat to enter that compartment, it can be actually avoided. Okay. Then you have other solutions. But these are not common. The common ones are basically, as I've said, multi-layer insulation. Then heat sinks. Heat sinks are very common. Heat sinks are nothing but it is basically you have seen in the computers that we have also in spacecraft to do and the heat transfer here normally happens through conduction. That means to say you have a CPU to basically heat pipe, you have a heat sinks. This is quite common in a satellite. Then thermal protection. Well, don't worry much about this. This is more into thermal protection system, ablative material. This is for capsules re-enter. Also thermal control system, but not for satellites. We don't use for satellites. Surface finishing, yes, indeed. For example, second surface mirror. Second surface mirror basically is the polished mirror with let's say solar panels will have actually these paints. Yes, you will have. This is quite typical for also satellite. This is also passive. And finally, you have thermal straps. Thermal straps. Just now you have seen huge. Let's say an equipment. You want to actually insulate the equipment. Use a Kapton, let's say insulator. It's just like a paper, just like aluminium foil. So you just wrap it. In order to seal that, we have also something called thermal straps to seal it. So it's just like stickers to seal. So that's they have a thermal straps. And you have a constant conductance heat pipes also. As I've said, heat pipes, when you don't put in the electricity inside, it is a passive mode. it happens actually to the surface tension and the capillary mode. Okay, so you have all these. More important again, paints, secondary surface mirror, multi-layer insulation, heat sinks. You have a thermal struts, filler. Yes, you do as well. These are for satellites. The rest you may have it like all this ablation. You may have it in capsules, re-entry capsules. Okay, this is passive one, and I've given the actual absorption and emission. Obviously, white paint, secondary mirrors, you have very good emission. Okay, and absorption, always black paint is going to absorb you more. So these are the two parameters. Is very important when you want to do thermal control or other thermal control design. You will see in our exercises. These are the two parameters that we always will use, and in order to calculate the temperature build-up or even the actual amount of heat generated within the spacecraft or satellite. So these are quite typical. This should be given because why? We should specify what kind of surface are there that we are dealing with. Okay, go on. Okay, now thermal control electrical system. Now remember, this is a rocket engine. I think you know. I think you will be exposed during rocket technology. Thermostat, of course, works with the temperature. You need to have the heat basically for it to actually function because you have two different materials involved. Now, attention need to be cartridge heaters and then cartridge heaters, and these are types of cartridge heaters. Now, cartridge heaters is important. Reason being, for example, I've told you that yes, indeed, bigger job is basically to reject the heat that we have on board. But don't forget, there are sometimes satellite environment becomes very cold, especially when you go into the eclipse. There are parts of the satellite never been exposed to the sun. It will be cold when you even go into the eclipse part. So now for those kind of parts, those kind of areas, you need to maintain, let's say 10 degrees. It drops down maybe to -5, -10. Then what you have this cartridge heaters basically to do heating instead of cooling. Instead of ejecting the heat out of your satellite, you are going to actually use our electricity, which we generate on board, to heat up that area, so that you can maintain about the temperature that actually is needed. So don't forget, not only to eject but also to heat up and to maintain the temperature regime that we have. Very good. Now, active. Okay, why active is important? High transfer capacity. Fluid will keep on flowing. Okay. Then extended basically transport distance. If it's a very long distance, huge spacecraft, space station, definitely is going to be active. You can't afford actually to do passive. Accurate control, you will have devices basically, the fluid flow will be actually controlled. High isothermal quality. Isothermal quality, that means what? Your payloads, temperature variation, it is so tight, so minimal. So minimal. So if you have a very tight requirement of plus minus temperature to maintain maybe optics, for example, then active control is important. But the problem is that, look at energy consumption, risk of leakage. This is another biggest problem. Perturbation, vibration. Pump is running. It's going to cause vibration. As it is to fly a satellite, it's so difficult. And plus, we are introducing, and it has been disturbed by all those elements, all those disturbance from outside, space. You will also learn that in space mechanics. All those space elements basically are being disturbed. Okay. Now, on top of it, we have introducing a disturbance inside the body, which is the pump. Pump is going to create jitter. Yeah, it's going to actually cause vibration. So we need to worry about this as well. So it's not easy. Not easy. Basically, most of the satellite we don't operate with pump. Let me put it clearly. Huge spacecraft. That means habited spacecraft. That means humans who's going to live in capsules, space stations. Yes, This is one of those things that we do. Dazzle system. This is just like a louvers. Is well, you have windows, the old windows basically. When you open up, just like this. When you open the window, that means you have a higher surface or contact area outside. When you close the window, basically you don't have much. So when you open up, you have a larger area, and according to that Stefan Boltzmann's law, you have a bigger surface in contact with the environment. The more radiation the more radiation can actually happen. That means more heat can be transported via radiation. And one phase loop, yes, this is, I think I will explain to you. It can be one phase, single phase, or it can be multiple phase, two phase in fact. Cold plates, afterwards you see what is cold plates are. Radiators can be body mounted. You will also see what is radiators. Radiators are basically, it can be actually with the motor which extends and then gives you a amount of surface basically for that radiation to occur when it's needed. So it has a steerable type also. If you don't need it, then you close it. So there are many types that you have. Electrical heaters that we have seen. Peltier heaters. This is something very unique. Peltier effect, it's something related to thermoelectricity. Now, when you have heat flowing through a particular material, if that material, for example gallium, it will actually have thermoelectricity. So that means the heat is being transformed to an electrical energy. So therefore the heat can be actually sort of well ejected. So that heaters also is available. Okay. But very not for satellites. You don't see much in satellite. Heat pipes, very common for satellites. You have a variable conductance, very typical, and you have a fixed conductance. These two. And this I will provide you the actual example how it is being embedded in a satellite, especially in that solar panels. Because solar panels become very hot. In fact, when the solar panels are very hot, the performance of photovoltaic cells also will be actually dropping. So you need to cool down it. Cool down. Pump, capillary pump, or two-phase. These are the options that you will have for the heat pipes. Two-phase, I've said two-phase, or even single-phase. Okay, one. So same like active control. You as a passive control, you have an active control now. Radiator. You have radiator operation mode. You have a conventional radiator. We will look at it later. Body mounted, steerable, and all sorts. Dazzle system is louvers. Imagine just like windows, opening and closing. Single loop fluid. You have heat exchanger. Cold plate. Single plate. That means that the water does not change the phase. Does not evaporate in fact. Two phase. You will have mechanically pumped, or you have a capillary pump. Okay, that means what? Passive. This is almost like a passive. Okay, it's almost like a passive. But when you have a two-phase loop, basically what you are having, the pump will be actually introduced. Then heat exchangers as well. Heat pipes, you have a variable, variable conductancy. This pipe, you have a heat pipe diode. You have also another types of heat pipes. So cryogenic heat pipes are basically a supercritical state of heat pipes. That means that whatever actually runs it into a supercritical state. We don't use much for satellites. Okay, we use I think variable conductance and fixed conductance. Heat pipes are very typical for satellites. Cryogenic system, cryogenic radiators. You can find this in rockets. You can find this as well. Thermoelectric devices. You have electrical heaters or patch heaters. This is for heating up. All you see here is for cooling. This is basically is for heating actually. Okay. So typical one for satellite, electrical heater. Cold place, you have a heater. Heater is what? It's just an electrical resistor. pump in electricity, you get heat, and then you can heat up the environment. Okay, this is cold plate, as you can see, single phase. All your equipment is on top, battery, your computer, onboard computer. Then what you have a thin passage, that means to increase the surface area. Fluid flow comes back, then you have the heat is actually ejected. You don't have this in a satellite, but you will have it in a huge spacecraft. So if you look at the internal design, these are the options that you have. All these are very, very different designs. Idea for all these kind of designs, V shape, you have W shape, rectangular, to just increase the contact area of the fluid flow. So simple ones is this. You have electrical box, thermal model, pumping basically the flow in and flow out. Heat is being transported out. So how much of heat is transported, you can calculate through MC data. The typical heat transfer formula. Okay, now this is a two-phase flow versus a single-phase flow. Now, obviously, what I'm trying to show here is that just like what is that? The performance graph that we have. If you look at it, now this is the space shuttle example that is taken here. Now, if you look at it, a pump, if you need a higher rate, basically a pump, you need to actually have the pumped loop. That means what? You have a pump inside, and if you don't have a pump inside, it drops tremendously. Look at the amount that actually you have. It's almost about 10 volts. Yeah? Almost about 10 volts. You have 100 volts in fact. 10 to 100 volts you have. So in order for it to have a higher capacity, or rather higher heat rejection. But again, satellites, you are not going to actually look at a pump option. We can have typical heat pipes, variable conductance, or basically fixed conductance. That's all we have. Okay, it's already good enough for us to operate. Okay, go on. Now, this is just to tell you that, okay, capillary pump heat pipe, how it actually works. Simple. Heat comes from where? Heat comes from the rigid body. That means your satellite. Heat comes here. There is a contact. How the heat comes here? Heat can come here through conduction. Okay, from equipment to here, it can be conduction, metal. Then this is called a evaporator. Then what happens that it actually evaporates the fluid. What we have here goes, okay, it goes there basically. Then it comes to here. This is condension. That means here at this state, the liquid becomes vapor, flow. Here would be cool down. When you cool down, vapor is cooled down basically, then it becomes liquid form, and you start the process again and again. So if you want this to be fast, you add a pump. You can add here. Yeah, you can add pump. So when you have a pump, so technically speaking, it's going to go fast, in fact. So when you have a pump, you can, if you have a pump, you don't have to actually have a vapor mode. You can just have the fluid mode. That means you don't have to vaporize that the liquid, because you already have a pump. So it's basically a single phase. When you have a pump, this is two phase. When you have an evaporator, when you have a condenser, when you see there's a condenser, it's an evaporator, is already two phase. Okay. But more importantly, okay, this capillary, when you look at capillary pumps. So capillary means what? Capillary, as I've said, if you cut this pipe, you see it will be grooves on the wall. So what exactly happens when they heat up? The liquid gets heated up, then turns into vapor. Vapor gets attached to the so-called grooves. It's like a capillary. And the flow starts. Okay, that's how actually it's called capillary. So it's helped by the actual design inside, and nothing, no electricity whatsoever. It is just the design inside. So that, and you can have, as I've said, you can have passive or active thermal control using the system. Okay. Again, remember, if you have pump, you don't have to have two loops. you can just have single loop, fixed pump. The fluid is actually recirculating to transport your fluid. Okay. So transport distance basically can be up to about 10 meters. Distance is quite good. Multiple set points within one degrees. That means 1 degree of temperature. Basically, you can have cooled or rather can maintain. Capillary pump or pump. These two you can use pump. You don't have to actually use pump. It depends on the options that we have. Okay, how much you want. But again, satellites avoid pump. So we have always basically a single loop where you can have a flexible conductance, no problem. We can have a fixed conductance, no problem. But we will not actually have pump. Okay. Lower weight basically, and then mechanically pumped systems is low cost also. When you don't have the pump system, it's going to be low cost. Okay. Radiators. What is radiators? Radiators basically it is going to give you an extra surface. The surface is going to actually look at outside of your spacecraft, provides a radiation surface. So body mounted, increase the surface, then heat is dissipated. You can imagine, you can think, that means this is the external. Inside, this is a capsule. So inside, you can have heat pipes. Okay, go on. Before this. Okay, assume this. Assume this is actually a radiators are here. Means coolant comes here hot. It comes here hot. Then get exposed to the radiator. Radiator cools it down. So how that heat is transported from here, this spot, to out is radiation. Go on. These are the shutdown, but these cannot just exist just like that. At the back there is cold plates. It could be heat pipes that you have. Depends on the system that you want, transport system. This is basically exposure system. You call it exposure. You can call it exposure. You're exposed to the outside to have a surface so that heat can be radiated out. So you have a lot of design. You can steerable, but for satellites basically is practically is just a space that you have, or the walls of satellites itself is going to actually act as a radiator in that sense. Okay, these are for huge. These are capsule, human capsule. Okay, go on. Okay, you have, look, this I'm giving you shuttle type radiator. You have basically heat pipe radiator, and you have a space station radiator. It's so huge. This will be a pump. So what it means that heat pipes, okay, heat pipes, radiator is a fins. All these are fins basically to increase the surface area so that radiation can happen. Now, more importantly, what you need to understand here, all these radiators are basically ejecting the heat with only one mode. Stefan-Boltzmann's law. That's the only way we can reject this. Before this, please. You see, here is all space. Only way I can reject heat from inside is the radiation. So I need to have radiators. Okay, go on. Okay, go on. So start. Okay, now this, as I've said, I've mentioned to you, the most complex thermal control system is even much more complex than the satellite itself. It's basically our space station. Is very, very complex. Okay, you will have basically active thermal control, external thermal control. You will have also passive thermal control. This is just basically for you to just have a look at it and to study a bit. I've given you all those abbreviations around here. So even look at the amount of panels they have. Now this is going to be also a heat source for the body. Good. Bigger panels, you generate more electricity, but at the same time you also have problem with the heat. So we need to, in satellite there is there's also a problem. So more often than not we use heat pipes basically to cool down the system, especially the panels, because panels is so huge sometimes it actually collects sun, rain, at the same time it also collects the heat, the solar flux. Have a look at it. I've given you all those evaluations also. Okay. Thanks. Then we can actually proceed with some exercises for you to understand how can we use all those formulations that we have and how to estimate our heat in a spacecraft. Thank you.